thumbnail. That thumbnail was great. You know what that thumbnail was? Great. Thumbnail. It's a new iPad. Look at this. This is beautiful. Purchased this earlier today with some of my Fuse Flex funds that I have for doing the fellowship that I'm a part of for blended personalized learning. It's pretty great. So big thank you, Highlander Institute, for the opportunity. I don't really have to sell this or anything, but thanks. Appreciate it. Oh, we got 6 fillers. Hi, Trevor. How are you tonight? Just let me know if everything's going good in the chat. We've got some things going good. We're not inverted. Volume's working good. I assume everything is good. Cool. I'm good. Thank you, Trevor, for the confirmation. All right, let's jump into the excitement of 3135 live review. First of all, I just wanted to bring up the topic list. Let me just pull it over here. And topic list. Okay, so topic list, we talked about this a little bit in class, but you know, the first 10 bullets are just everything from the first quiz you guys are responsible for. So that's the definition of the derivative, the alternate definition of the derivative, mainly in the context of being able to recognize it. Okay, so you don't need to essentially do the definition of the derivative anymore, but know if you're asked to solve a limit involving the definition of the derivative, that you're just asked to define the function, find its derivative, and then of course take its derivative at the value. So just know that. Tangents and normals and graphs of derivatives, and of course the whole differentiability implies continuity idea, finding the values of two variables that make the function continuous and differentiable. So that was a big idea on the last quiz. Make sure you guys review that. Know how to find the derivative with a calculator, know how to make the graph of a derivative with a calculator, all that stuff. So that's all the old stuff. So transitioning into the new stuff, which is know the product rule, know the quotient rule. Make sure you know how to identify the structure of a function if you know how to use the product and quotient rule. So that's if I ask you any follow-up questions in regards to a function that you would need to know its behavior, what is it doing at certain values, okay? Know how to find the second derivative or higher. Know how to evaluate a derivative for some values. So for example, this is one from the textbook. You had to take the derivative of uv. That's just low d high, high d low, so bottom v times derivative tops u prime. Minus u times v prime all over v squared, and then you just plug these values right in and boom, you got it. Study your particle motion notes. I mean, that's a really big part of this assessment, okay? Making sure you're familiar with those. They are, of course, right here. If you go here, you've got your particle motion helpful notes right here, very important. And of course, your help with trig for 3.5 if you need some help with trig. Know how to analyze a velocity graph, know how to find marginal cost, marginal revenue, marginal profit, and know the meaning behind it. So what are you actually doing when you plug in the value? And know how to actually find the change in the cost, the revenue, or the profit. If you just find, the cost, for example, the cost of the new value minus the cost of the original value. And last but not least, know the derivative of the 6 basic trig functions and know how to derive them. So I could ask you to derive any of them. Sine and cosine are a bit harder. You have to use your angle sum formula, but cosecant, secant, cotan, and tangent are very simple. You just use the quotient rule to find their derivatives. All right, so we're going to scooch this out of the way. We're going to bring this back up. Oh, we got to log back into it. Okay, airdrop active. Oh, airdrop is active. Oh, we'll try that again. Try that again. And then I got to pull the chat up. What's the matter? You don't like that? You're not airdropping? There you go. Okay. Let us move this over a bit. You don't want to move over? There you go. Maximize it. We've got the graph ready to go. And we'll check in with the chat, see how everyone is doing. Hi, Matt. How are you? Hi, James. Nice to see you again. Owen, good evening. Matt, sense. And Trevor, awesome picture. Thanks. Yes, great desktop background for the making. Okay, so that's essentially what's going to be on this assessment. Let's get into taking a look at some things I prepared just to make sure that we're all feeling familiar with this material. The first of which is just a notation slide, making sure you guys are familiar with the notation. There's a lot of different types of notation for derivatives. The main one is, of course, you've got your y prime. Y prime indicating the derivative of a function. It's a quicker notation, so it doesn't really tell us what the dependent or the independent variable are. It doesn't tell us what the respect is, but it's a quick way to derive it. Dy dx is the most common notation for derivative. It basically stands for the derivative of the function y on top, and x is your respect on the bottom. So that's the most common notation. df dx is just if you're differentiating a function f of x. You can also indicate d dx in front of any function you'd like to differentiate. That's, of course, indication of the derivative. Okay, so just be familiar with those different ways to differentiate. And of course, when you start getting to higher derivatives, you can do the second derivative of y with respect to x. So that is notation for the second derivative. Specifically the second derivative of the function y with respect to x twice. All right, so just be familiar with that. The next big theorem we've got, of course, is differentiability implies continuity. This was a big theorem on our 3132 quiz, making sure that in order for differentiability to be considered, you have to first have continuity. So when we have our piecewise functions and we try to find those missing values for a or b or whatever, you have to make sure that continuity is first established, and you must use appropriate notation. So we're talking about the limit as x approaches some value, we'll call it a, from the left of f of x must equal the limit as x approaches a from the right of f of x. Okay, so this is the standard continuity definition. And if you have some piecewise function that's also defined exactly at a, so like when x equals a, you would need to make sure that that value f of a is also shown to equal your limiting values. Most of the examples we do together, the piecewise function has a greater than or equal to or a less than or equal to, so that that condition is kind of left out because it's redundant to prove that it's equal to itself on one side, so to speak. But if it's defined in three pieces, meaning less than a, greater than a, and equal to a, you would need to show that the function value equals the limiting value. That's how you would achieve continuity there. Okay. All right, we're swinging along here to product and quotient rules. Got to know your rules here. The product rule, of course, the derivative of two functions inside of a product is equal to the first function times the derivative of the second plus the second function times the derivative of the first, and then you simplify accordingly, okay? It's notable to add that if you ever have a constant inside of your product, you can pull the constant or multiple constants out, differentiate using the product rule, and then put the constant back in through multiplication, okay? So sometimes that helps clean things up. And of course, you've got your quotient rule, which I always say low d high minus high d low all over low squared. And that's, of course, the low being the bottom function, d being the derivative, and high being the top function. And that's your quotient rule. All right. Oh, wait, did you get a new iPad? I did get a new iPad. Just tonight. I actually haven't set it up or anything. I have a case and a screen protector I have to put on it, but I didn't have any time tonight. So I still, this would be the last time we're using my daughter's iPad mini. So it's been a good investment for our sessions so far, but it's time to upgrade to a space that's a little bit larger than the Apple Pencil itself. So yeah, that's your product and your quotient rule. Got to make sure you know those. Of course, look at all of your derivatives in 3.3. You've got to know your power, your negative power rule. You've got to know your constant multiple, your sum rule, your difference rule, all those rules for derivatives, okay? May you please do an example of a product rule where you pull out a constant? Yeah, sure. I mean, all right, let's just, before we move on, do one real quick. I could add a page right here, and I could ask you to find the derivative. Find d dx of y equals, let's just do like on the review guide, I gave you something like 3 cosine x times 4, and we'll say secant x. And if you wanted to take the derivative of this thing, you could do the product rule where this right here is the first function and this right here is the second function. Or you could just take out the 3 times 4. 3 times 4 is 12. So before I do anything, I'm actually just going to do a 12 here. And then we can do cosine x. And then we can do secant x. But I know secant x is, of course, 1 over cosine. Oh, that's silly. That just makes the problem way too easy. Why don't we change it to a cosecant? Otherwise, there's no math to do. We'll change this to a cosecant x. And of course, cosecant x is 1 over sine x. And that's just a bit more fun. So now we can take the derivative with the product rule where this is piece number 1 and this is piece number 2, and we could just feed the 12 back in, or we could identify that cosine times 1 over sine is just cotangent x. Cosine over sine is just cotangent. So what I'm going to do is just use my power rule here on the cotangent, or not power rule, but just my derivative rules, and leave the 12 outside for later. So it's just going to be 12 times the derivative of cotan x. And if you use my Shack tip, cotan is a cosine over sine, has 2 trig functions, so its derivative has a square in it. So that means its derivative is going to be cosecant squared, but it has to be negative as well. So really, Ari, that's just taking the 12 and pulling it out for later, doing the product rule, or in this case, just the derivative of cotan, and then putting the 12 back in. And I could do one where you actually had to use the distributive property if you'd like, but the idea is I would just do my product rule inside here, and then I could just distribute the 12 or leave it factored afterwards. So you let me know if you'd like to see another one that's a little different with regular functions rather than trig. Okay, and then of course we get to our derivative of our trig functions. And of course we know the rules, the silly rules. First silly rule is that anything with a co has a negative derivative, okay? So anything with a co. So you take the derivative of cosine, cotangent, and cosecant, the derivative is negative in some result, okay? Then of course sine goes to cosine, cosine goes to sine. So that's easy. Tan and cotan, they get the square derivatives because they have 2 trig functions inside of them. They're sine over cosine and cosine over sine, respectively. And we know that secant and tangent hang out because they don't have any cos. And we know that cotangent and cosecant also hang out because they don't not have cos. They're the co-club. They're cool. And so then the derivatives, respectively, are negative cosecant squared, secant squared for tan and cotan. And then secant's derivative is secant x tan x, and cosecant's derivative is negative cosecant x cotan x. These 4 at the bottom are very easy to prove. In the event that you don't remember how to do one, let's just pick one randomly. So I believe I did tangent in the video, and we did secant in class. So let's do cotangent. So if y is cotangent, let's find dy dx. Okay? So we know cotangent, of course, is cosine x over sine x. So then we have to do the quotient rule to find the appropriate derivative. So we'll just erase the question mark and start deriving it. So it's the low d high, high d low. So it's the bottom. So it's sine x times the derivative of cosine. So the derivative of cosine is a negative. And of course, then it's just a sine x, right? So it's a co, so it's negative, and then the derivative of cosine sine, minus the top function, the high function. So cosine x times the derivative of the low function. Derivative of low function is just sine. Derivative of sine is cosine. So then we do over the bottom squared. Okay, so if I clean this up a bit, I have a sine times a negative sine, which is a negative sine squared x. And then I have minus cosine squared x all over sine squared x. Okay, and in order to simplify this, I'm probably going to need to use my identity in some capacity. So I'm just real quickly going to write that off to the side. That sine squared x plus cosine squared x is 1. So then if I need to get a negative cosine and a negative sine, I'm just going to multiply throughout -1. So I get negative sine squared x minus cosine squared x is equal to -1. So this is the value that is equal to the highlighted numerator. So then if I just plug -1 in the highlighted numerator, I get -1 over sine squared x. And I know that 1 over sine is cosecant, and I negative in front, so this is just equal to negative cosecant squared x, which of course is the derivative of cotangent x, okay? So we get the negative cosecant squared. Cool? Will, I think we can, unless a specific problem says to use the definition of the derivative, we can use this, right? Yeah, Trevor, we can use the shortcut throughout the test. The only time you can't is if it specifically says use the definition of the derivative, but even that is uncommon. Really, the extent of the definition of the derivative is your ability to see it in a problem and be able to solve a limit involving it. So more recognition rather than actual solving of the definition, okay? So definitely all we need. Okay, so let's keep moving. We've got position, velocity, and acceleration. Of course, as we go deeper, we're taking an extra derivative. Velocity is the position's derivative, and acceleration is the position's second derivative, or the velocity's first derivative. Okay, so just know notationally, position we usually use x of t or s of t, and velocity we use v of t, and acceleration we use a of t. A big important concept is the difference between average rate of change and instantaneous rate of change. So just picking velocity as an example, but this applies to all, average acceleration, instantaneous acceleration, average jerk, instantaneous jerk. But considering velocity alone, the average velocity is just simply y2 minus y1 over x2 minus x1. That's a bad y. I'm going to fix that one. Specifically, it's just the displacement over the time. And so we calculate that by doing the y value of the function minus the second y value of the function over the x value minus the x value. But it's really important to understand that average velocity actually uses the position. So if I took this and I took it a step further, I'll just put it up here for a second. What average velocity really is the position at some value b, let's say, minus the position at some value a divided by b minus a. S of t, of course, being the position function. So average velocity, when calculated, does not use a derivative. However, the instantaneous velocity uses the derivative of position. Okay, so you just plug the value into the derivative of position, and you've got your function. The difference is this. Average velocity is over an interval. Okay? Average velocity is over an interval. It has to have a beginning number and an end number. Whereas instantaneous velocity is at one value only. You're calculating the velocity at one moment in time, instantaneously. So average velocity uses an interval, and instantaneous uses one value. Okay? Average velocity uses position because it uses the function before it. So average acceleration would therefore use velocity. It would be a velocity value minus a velocity value divided by x value minus x value, or time. Whereas instantaneous just uses the velocity function, okay? So we'll do a problem like that in the notes, and we do a couple in the practice test as well. But just be aware that that is a thing. So if given limit already in the definition of the derivative, could you state that it is the derivative of whatever function and then use the shortcut, or would you have to solve the limit? No, Trevor, you can establish the function and then use the shortcut to your heart's content on the established function. So typically, I just need an answer on those questions. You can get it by any means necessary. Okay, let's take a quick turn and talk a bit about profit, specifically econ in general. Okay, so I just chose profit because it's the most common one we look at. Remember that profit is the only one you actually have to solve for sometimes. It's the revenue minus the costs. So revenue is all the money coming into a company, and cost is all the money the company's spending. The profit is therefore the revenue minus the cost. And marginal profit is basically a measurement of one additional good. Okay, so if we wanted to figure out, if we're selling 100 TVs, and we wanted to see would I be making a profit or losing money if I decided to produce one extra TV, 101st TV. And so therefore, in order to examine that, we actually just plug 100 into the derivative of profit. And that measures the rate of change right at 100, which would give you a nice indication of the change in profit for the 101st item, okay? So by plugging 100 into the derivative, you're actually getting an estimation for the 101st item. Just an estimation, not an exact value. Remember, you can actually find the actual gain in profit by just simply taking P of X plus H. So in this case, it's just going to be the profit of 101 televisions, or I like to say televisions, but whatever, items, minus the profit of producing 100. And very clearly, this will give us the actual value of that 101st item. Because if you take the profit of making 101 of them, and you minus the profit of making 100 of them, then obviously what you're left with is the profit of producing the 101st item, okay? So why does marginal functions exist? Because they're very easy to calculate for a large scale, all right? Oh, right. No problem, Trevor. Happy to help. So that's it for notes and such. The rest of the slideshow is just problems that I've kind of pulled together and thought they'd be fun to practice. We're going to start with a very famous particle motion problem. I believe this is the exact same function as the class notes. It's just a very interesting function because the zeros are like almost misleading, so I wanted to look at it again. This particular problem is measured in feet per second, and I know that's going to bother Matt. Sorry, Matt. I know you like meters per second. But in this particular problem, we're going to use the position function to be this cubic polynomial here. In question A, we're going to get the actual function in the calculator. So I'm going to plug in 16x to the third power, and we're going to minus 112x squared, and we're going to plus 160x. Pardon me while I just check my phone, make sure it's not a note. We're good. I want to make sure it wasn't a remind or anything someone needed help. So this is the original function. And the reason why I really like this function is because it has really misleading function values. Look at this. It looks like it goes from 0 to 64 feet after 1 second. Or is it seconds? Yeah, seconds. And then back down to 0 2 seconds. But we can't be sure that that is the only distance that's accumulated between 1 and 2, okay? Of course, what you'd have to do, the only way to actually figure this problem out exactly is to find out where the particle changes direction. In order to find out where the particle changes direction, you need to set the velocity equal to 0. So if you do that, I'm going to just do that off to the side here, okay? The velocity equals 0 when t equals, and I'm going to go ahead and solve this. This is a calc-active problem because this function is real nasty. So I've got my original function y equals. And what I'm going to do in y2 is I'm going to graph its derivative. So I'm going to go to math 8, which is derivative. I'm going to graph this thing for respect of x, and I'm going to do vars, y vars function y1. So I'm graphing the derivative of y1, and I'm going to do it for all values of x. Okay. Now, for the time being, I'm just going to shut off y1 so I can get a pretty good look at this particle. Let's do the window. So I need to find the zeros of the derivative. So I don't really care much for y. It can just range from -10 to 10 because I want to figure out when y is 0. But x, I need to be a little bit better at. We don't really need negative values. So what I'll do is we've got 2 zeros. Wonderful. And we know, of course, this thing's quadratic because the original is cubic. So I know there are going to be 2 solutions to its derivative. Let's find them. So we're going to go second calc, 0, which is number 2. Left bound, let's see, that's not where I want to be. I want to go over to like maybe below +1. I'm going to find the left one first. So maybe like, there we go. That was a good one. Left bound is like right there. That's what I want. Left of the 0. Then I'm going to go to the right, and I'm going to do a guess, which I'll just go back here and kind of try it. And it looks like we're good here. So the first 0, which I'm going to go 3 decimal places, is 0.880. So 0.880. Okay. And then I'm going to find the second one. So I'm going to go calc 0. This time we're going to go over find the right one. So I'm going to go over here. It looks to be around what, 1, 2, 3, between 3 and 4. So I'm just going to go over here, and I'm going to do left bound to be over here. And then I'm going to press the right arrow again, and now I'm up to the right of it. So I'm going to press enter and then guess whatever. It looks like the second 0 is at 3.786. And t equals 3.786. Okay? And this is imperative in order to get this question right. Because now what I know, finally, from 3.786 to infinity, will then be moving the same direction. So if I'm calculating the total distance from 2 to 5 seconds, I know that from t equals 0.880 all the way up till 3.786, that the particles go in the same direction. So from 2 to 3.786, the particles going the same direction. So I really need to figure out how much distance was accumulated in the interval of 2 to 3.786. And I also then need to figure out how much distance was accumulated from 3.786 all the way to the end of my interval, which is 5. Okay? And in order to do that, I'm going to use the position function, which is y1. So I'm going to turn y1 back on, and I'm going to turn the derivative off this time. And we're going to go back to my table. I'm going to check in with the chat real quick. Let's see, why is it that the derivative of profit doesn't give you an exact value for how much more profit you'd make on the function? Well, it's just because the value P prime X changes between 100 and 101. Yeah, it's really just because it's an estimation. It's using the tangent exactly at 100 to calculate the value of the function exactly at 101. So it's really just an estimation of the slope. It's not meant to be an actual calculation. The function could actually have a change in slope for the next value, or even the next 1/10 or 1/100th of a value. Could have a different slope, it could have a different tangent, therefore leads to a different slope. But that's why the rate of change at 100 is really just giving us an estimation for the value at 101, because the derivative is changing. Instead of solving for zeros and a velocity, could you also use your calc to find the extrema of the position? Yeah, Trevor, you can, but remember, I find it much easier to find the zeros rather than an extrema, because I don't have to worry about the y values of my window. That's honestly where people have the most trouble, is how high or how low do you have to go to get limbo. Well, how high do you have to go to get alpha x? You know, the one we did in class, I believe it came out to like 2 difference of squares. So you could just get the values really quickly that way. And then, you know, find the distance, you would just plug the values into the original function. So this interval right here, for example, what I would do if this was a no-calc problem is I would plug 2 into the original and get a number, and plug 3.76, which would not be 3.786 if this was no-calc, into the original to get a number. And I'd find the accumulation of values, in other words, like the high minus the low, and then I'd use that as distance. So it's not any different. It's just on a no-calc problem, the values are much easier to handle and to calculate by hand, but it's really no different in process. Okay. Thank you. No problem. Will, happy to help. Okay. So let's now find the answer. So let's go to the calculator. What I need to do is I need to find the accumulation of distance from t equals 2 to t equals 3.786. So what I'm going to do here is I'm going to actually adjust my window smartly. I'm going to start at 2, and I'm going to go all the way up to, or I'm going to go up rather by, well, actually, let's go up by 1.786. And I think this will give me what I want. I wanted 2 and 3.786 to be on the same viewing window. Okay. So now what I know is that the particle from 2 to 3.786 is going to go exactly 131.3 units. We're ignoring negative values here because I know that I want a distance which is all positive units. So the answer in this interval is 131.30 units. Okay, so that's the distance from 2 to 3.786. And then what I'm going to do is I'm going to actually go from I'm going to start this time at, let's see, I need to go 3.786 to 5. Now we know real quick, I'm just going to go back to my table here. I'm going to write this down so we don't have to look again. It's 131.3 at 3.786. So now I'm just going to go to my table. I'm going to look, oops, my table's set. I'm going to start this thing at 5 this time. And I can just go up by ones, doesn't really matter. At 5, it goes back to 0. Oh, that's easy enough. So I know that it went from negative 131.3 back to 0. That's another 131.30 units of distance, because of course I'm going from negative 131.3 down to 0. So I know that from 2 to 5, it went exactly 262.60 units. And we'll just circle that. Okay, so using the calculator, the only thing, the only area I would urge caution is making sure you set the velocity equal to 0, finding when the particle changes direction, then calculating your function values, okay? Without a calculator, plug them into the original. With a calculator, just use the calculator's table to help you find them. All right, so that's A. Let's see. When I do VT, I get t equals 2 and t equals 5 for A. Let's see, Hugo, are you talking about this function right here? Yep. When doing 5 is answered, because we just used the calc to figure them out. So all I did is I just plugged the original in here, and then velocity in here, and then I found the zeros of y2. So just check again, plug them in the calc and see. Should come out to those function values, those decimals there. Thanks, no problem, Ari. And how do you get the distance from that? So how you get the distance from that is really just the higher value minus the lower value. So if you wanted to, you could always just take whatever number was bigger and subtract it from whatever number is smaller. keeping in mind that you want the absolute value of these numbers. So the fact that we went from 0 to negative 131.5 or 0.3, that's an accumulation of 131.30 units of measure. So making sure you take absolute value of those numbers and you subtract them, or in essence, it's really just the absolute value of the difference of the numbers, because that would give you the positive result. All right. Do I do SFI by SFI? Yeah, Hugo, that's exactly what you do. So I think we are caught up in the chat. Let's keep going. Intervals in which the object moves left. Okay, well, this isn't too bad. We've already established the points at which the velocity is 0. So I know that at 2, or rather at 0.880 and 3.786, the particle is going to change direction. So stop and then change direction. So I know that I need to make a sign chart of the derivative. I need to test 0.880, and I need to test, what's the other one, 3.786? So all I really need to do is, using the velocity, this is for the velocity, look at the calc and find the signs of the velocity. So I'm going to go back and I'm going to try between 0.880 and 3.786, I'll choose 1. It's negative. And then, of course, if I choose a number greater than 0.786 or 3.786, it's a positive value. So I know that the particle is moving left anywhere the velocity is negative. Okay, and that occurs between 0.880 and 3.786. Okay, so that would be my solution to letter B. Particle moves to the left or down depending on direction when its velocity has a negative value. All right, so that's what I would do for part B. All right, same function, a couple more questions. I just didn't want the slide to be too overwhelming. So let's try now the average velocity in the first 5 seconds. Okay, so the average velocity in the first 5 seconds, remember, does not use velocity, it uses position. This question is actually asking you to find the velocity, the average velocity from 0 to 5, correct? First 5 seconds means 0 to 5. So what I would do is I would find the position at 5, subtract the position at 0, and divide by 5 minus 0. Just y2 minus y1 over x2 minus x1. So I'll use my handy-dandy calc for help. I'm going to go back to y equals. I'm going to turn on the position, and off goes the velocity. Back to the table. The position at 0 is 0, and the position at 5 is also 0. So this is just equal to 0 minus 0 over 5 minus 0, which is 0. And the unit of average velocity is a rate of change. So it's, in this case, feet per second. So it just turns out that the average rate of change from 0 to 5 is 0 feet per second. Okay. Acceleration is negative on 0 to 7. So if I need to figure out when the acceleration is negative, I can either find the moments that the velocity is decreasing, or I can just simply find the derivative of velocity and find out when it's negative. So I think I'll do that because that's easiest. So let's go here, and in Y3, I'll plug math 8. We'll do respect x, vars, y vars, function y2, differentiate y2 for all values of x, go back to the table. So on 0 to 7 is the acceleration positive or negative? It looks like, so it looks like we're going to have to do a bit of work here. We're going to have to figure out what's happening on this interval. So it looks like the acceleration is going to be negative to start with at you know, it looks like all the way up to 2, and then positive from everywhere after that. So I think it'd probably make the most sense. We could find the values in which the acceleration is equal to 0, and then we could determine it a bit more clearer. So why don't we do, I don't know why I just hit graph. We're going to have to adjust my window. Let's go back to my, well, maybe not. Let's think. This thing is just linear, right? So I think there's only going to be one value. I guess we're okay. So t is going to be whatever that is, and my calculator is still loading. If you press second on while your calculator is trying to load, it pauses. See these little dots? That means I just paused my calculator. Now I can do stuff while it loads. Oh, come on. You don't want me to calculate the 0? Fine, fine. Continue to load. I'll check the chat. When we do Q&A, can we do number 31 on page 124 from the textbook? If it says find the derivative of that thing. Yeah, we can totally do that, Ari. We've got a little time left. I mean, I'll make sure I save a little time for some extra problems as well. Oh, I never unpause this. That's real awkward. All right, go. Graph the derivative. So I can find its, it's just taking too long. Nope. Oh, it's done now. All right, cool. 0, left bound. We got to get less than 1 or anywhere between 0 and 1, something around there. So let's keep going. Let's keep going. There we are. We dipped below. And we're going back the other way. And then we'll do a guess. Acceleration, it looks like it's going to be 0 exactly at 2.33. So acceleration is 0 when t equals 2.33. So that means if I make a sign chart for acceleration at 2.33, it's going to change. And we already know it's going to change from negative to positive, because from 0 to 2, it's negative. And then from 2 to infinity, it's positive. So it asked me, when is the acceleration negative on 0 to 7? So the answer is between 0 and 2.33. It's notable to add that we're not going to negative infinity here. We would stop at 0 because time can't be negative. So I would say that the answer is, and I'm going to just, I guess I'll put it right down here. The acceleration is negative. You know what? I'll just erase this part. And we'll just put 0 to 2.33. For particle motion, I typically always use parentheses. I never really put anything in brackets unless it's a time interval. I'm just including the endpoints on the interval. But acceleration, velocity, position, I usually use open circles for everything. Okay. Last question, is the particle speeding up or slowing down at t equals 2? All right, a wonderful question. There are a couple of ways to answer it, and I'd like to kind of look at it a couple of different ways. First of all, in like we talked about in class, a particle speeds up when its velocity and acceleration are working together, meaning they're both positive or they're both negative. And a particle slows down when they are opposing each other. So one is positive while the other is negative, and they kind of, as a result, work against each other. So if I were to simply just find the velocity at 2 and the acceleration at 2 and compare their signs, I've got my answer. So this is acceleration. Acceleration is negative. And if I go back to velocity, at 2, it is also negative. This is enough to conclude that the particle is speeding up because they're working together. So since v of t and a of t are the same sign, the particle speeds up. Okay, so that is a particle motion question. I tried to do as many parts as I could think of, but that's really got a lot of good stuff in there, okay? How much of the quiz is calc active? I'd say it's about a 60-40 split this time. Thanks, Matt. So that's kind of what we're looking at. Okay, let's do maybe about like, oh, there's the solutions there. Let's do maybe about like another 10 minutes, and then I'll kind of pause for some Q&A, and we'll see how everyone's doing, okay? I just grabbed some problems from the textbook that are fun, from the like the AP review or the quiz prep sections at the back of each chapter. This one says, true or false, the derivative of pi cubed is 3 pi squared. Justify your answer. Well, what's my respect? My respect is x. Do you see any x's in the problem? No. There are no x's in the problem. And so therefore, there's no variables. And so this pi cubed is just a constant. So its derivative is just 0. So that's false. That's false. Do a circle right there. The graph of f of x equals 1 over x has no horizontal tangents. Well, horizontal tangents would be the derivative is equal to 0. So I'd say if I took this function, which is x to the negative 1, right? If I move the 1 over x, I move the x up top, and I calculate its derivative, so f prime x is equal to, the constant comes down, so I have negative 1x, and I must reduce by 1, so negative 2, which is equal to negative 1 over x squared. And the question is, can I set that equal to 0? Is negative 1 over x squared ever equal to 0? Well, no, because the only way a rational can ever equal 0 is if the numerator is equal to 0. And since negative 1 can never equal 0, this problem definitely cannot have any horizontal tangent. So that's true. That's true. Negative 1 over x squared can never equal 0. Okay. What's this one? Find a double derivative? Wow. Okay, sure. So let's find a first derivative. So first derivative is derivative x is 1. Derivative of 1 over x, we just did that, right? It's negative 1 over x squared. Actually, you know what? Since I have to take another derivative, I'm actually going to leave it in unsimplified form. We'll just call it negative 1x to the negative 2 because I'm going to have to take a second derivative. Second derivative is equal to derivative 1 is 0. Derivative of this, the number comes down. Multiplication yields positive 2, x to the negative 3, which is 2 over x cubed. So just practicing my 2 over x cubed, practicing my negatives there. And that, let's see, that's not the answer they have. They have D as the answer. What happened? Did I lose a negative somewhere? 1 minus 1 over x. So 1 minus x to the negative 1. Oh, let's see. I think I wrote it wrong. This is x minus x to the negative 1. So the negative would come down. Yeah, I did it. This right here should be a positive. Sorry about that. And then that would make this negative, which would indicate that would be negative. Yep, so it's actually choice D. Choice D. I did not do my first negative. I never wrote my first negative down. So that that's the answer there. So that's not too bad. Okay, let's try some more. Let's see. Which of the following statements are true about the absolute value of x plus 1? I got a hunch there's a corner here. Absolute values always have corners. So f is continuous at negative 1. Yeah, I think that's true. This is just an absolute value curve, right? What this thing is, this is just an absolute value curve moved to the left one space. So this is what f of x is. This is f of x. So is it continuous? Yeah, totally continuous. Is it differentiable at negative 1? Well, here's where I don't think it is. Because at x equals negative 1, right here, we're at negative 1. That's when the slope changes from a negative slope to a positive slope. And I know then the derivative is just going to change from negative 1 to positive 1. And therefore, we'd have a jump discontinuity on the derivative of negative 1 there, at negative 1 of the derivative. So that's not true. So that's not true. Nope. F has a corner at x equals negative 1. Yeah, that's absolutely the type of differentiability there. So that's true. F does have a corner there. So I think it's going to be D. It's going to be D. We have a corner at the value negative 1. All right. Okay. Let's see. If the line normal to the graph of f at 1, 2 passes through negative 1, 1, which of the following gives the graph of which of the following is the value of f prime 1? All right. Well, let's see what we've got here. We've got a line normal to the graph of f at 1. So 1, 2. So I know the point 1, 2 is on f. Passes through the point negative 1, 1. Well, I think what I could probably assume is the normal contains both of these points, right? So why don't I find the slope of both of these points? So what if I do y2? So the slope, we'll do straight slope. Slope of the normal, is equal to 1 minus 2 over negative 1 minus 1, which is equal to 1 minus 2 is negative 1 over negative 1 minus 1 is negative 2. So I'm going to get a positive 1/2, which means that the slope of the tangent is equal to the opposite reciprocal of 1/2, which is negative 2, So interestingly enough, I now know the slope of the tangent, and I also need the coordinate of the tangent, and it's going to be the same coordinate of that the original is tangent at it, which is 1, 2. So I know the 1, 2 is going to also be on the tangent. So I think that's enough information to see if I could build the tangent and then find the slope, although I'm not sure I need to, because this question is actually just asking what is the slope of f at 1. Well, interestingly enough, I know that the slope of the tangent and the slope of f happen to be equal at the point of tangency. So I know the answer is negative 2, which is A. I don't even have to actually build the equation of the tangent. I'm just literally finding the slope. So that's what I would do for that one. All right, here's another couple ones. Which of the following, time check 18, we're good. Check and chat real quick. He says 60-40, thanks, no problem, false. Will the calculator portion of the phone be in 3.4 material? It's tough to say, Dara. I tried my best to make sure that the calculator there's a particle motion calculator question on the review guide, and there's a particle motion no calculator question on the review guide. So you can get a little practice with both. It's honestly, it's 50-50. You know, on the AP exam, on the test, you could see it on either section. I don't think I'd give you 2 particle motion questions, but I may ask you like 1 particle motion question with like a couple of pieces on a no calc and 1 particle motion question with a couple of other pieces on the calc. That way you get a little experience kind of with both. But just be aware if it's a function that is going to give you nasty roots, I wouldn't expect you to go crazy to find those roots. Just plug them in the calc. That'd be on the calc section, okay? So I hope that clarifies that. Let's try another one. It is 9:19. We got time for maybe like 1 more. Let's see. We've got those ones. We got tangent and double cosine. Yeah, I don't know. Any preference? We can do maybe 1 more of these, or we'll do both if we have time, if not many people have questions. But why don't we just start with 47, let's say, and then we'll see if we could do 48 a little later. Which of the following is the equation of the line normal to sine x plus cosine x at pi? Okay, so if we do y prime, we need to find the derivative of sine x, which is just positive cosine x. And then the derivative of cosine is negative sine x. And all I need to do is plug in pi. So plug in pi, so I get y prime of pi is equal to cosine pi minus sine pi. Okay? And I know that cosine pi is -1, and I know that sine of pi is 0, so that's the slope. So all I need to do now is find my normal slope. So this is the slope of the tangent. Slope of tangent. So the slope of the normal is the opposite reciprocal, which is +1. So I know the slope of the normal is +1, and I now need to figure out the coordinate point, and then I can plug it into y minus y1 equals m minus x1. So I just plug pi in the original. So I'm just going to do that up here just so I save some space. So pi goes into sine x, and out comes a 0. Pi goes into cosine x, and out comes a -1. So I believe pi comma -1 would be the coordinate because the sine went away and cosine pi is -1. So I get pi comma -1. Okay, so now I just plug it in. So it's y minus y1, which turns into y plus 1 equals, because y1 was -1. And then I'm going to do m, which is the slope of the normal this time, because it's asking me to find the normal. The slope of the normal is 1 times x minus x1, which is pi. So I get y plus 1 equals x minus pi. And if I minus 1 both sides, I get y equals x minus pi minus 1. X minus pi minus 1, which is letter B. Letter B. So that would be a typical normal question, just with some trig functions thrown in. All right, so I think we did a good sampling of everything tonight. We'll pause there. We can certainly do some other ones if you guys want. I'm going to add a page, and I'm going to look for Ari asked me a question a little while ago that I'd like to do. And so we're going to go, let's see, Ari, it's in the bookwork you said, right? I'm going to go back to Ari's question. So Ari asked for, oh, that's too far back. Here we go. Number 31 on page 124. All right, that's what we're going to pop off on right now. Number 31 on page 124. So we're going to go to textbook. We're going to bring it over here for just a quick second. Page 134. I'm just going back to my chat. Page 124. Page 124. We are at page, too much. Page 124. Almost there, almost there, almost there, almost there. And 124. And we are doing problem number 31. Okay. Let's do it. So it says y equals root x minus 1. So I'm going to bring back it. We don't need the calc anymore. All right. So in order to solve this problem, I think the easiest way to do it is to translate these these radicals into rational exponents. So I'm just going to call this x to the 1 over x to the 1/2 power plus 1. And I think that's a little bit easier to take the derivative of. Okay. So let's do it. Y prime is equal to. So this is the quotient rule, right? This is the quotient rule. So this is low d high, which is the bottom function, times the derivative of the top. Okay, well, luckily for us, the derivative of -1 is going to go away. So the question is, what's the derivative of x to the 1/2 power? Well, if I use the power rule, that's going to be power. Right, so that's the derivative of x to the 1/2 power. It's 1/2 x to the -1/2 power, because I'd have to subtract 1 from the power of 1 over 2. 1/2 minus 1 is -1/2. Minus, I'm going to scooch this over because I'm definitely going to need some more room. All right, so now we're doing low d high. Now it's high d low. So it's high, which is x to the 1/2 minus 1. Divided by the derivative of the denominator. The derivative of x to the 1/2 power and plus 1 is the same thing as the derivative of the top. It's just 1/2 x to the -1/2. Reason being because the derivative of the plus 1 just goes away, and so then I do power rule again. All divided by square root of x plus 1 squared. Okay, so that looks to be everything that I needed to do. Now it's just algebras. That's the only calculus involved in the problem. Now it's an algebra battle. So let's see if we can simplify. So x to the 1/2, I'm going to put the radical back. So this is radical x plus 1 times 1 over 2 radical x minus radical x minus 1 times 1 over 2 radical x, all divide radical x plus 1 squared. I'm not quite sure where I need to take this. That's the derivative. You know, I've successfully completed the problem. Perhaps maybe getting rid of the fractions within the fractions. So I could probably achieve that by just multiplying the 1 over 2 rad x throughout and then maybe trying to get a common denominator. You know, I'm a little worried about taking this problem too far. I don't know what we need to, or how simplified we need to get it. Let's maybe just do a bit more and we'll see kind of where we're at. So if I distribute this, or I could actually just factor it out, and then I'd have the terms being subtracted. Maybe we just try that first before we multiply. What if we factored? So what if I factored this out of the numerator? So this term, if I did this, I'm going to use like a red. This term would lose this, and this term would lose this. So what's left is radical x plus 1 minus radical x minus 1. Okay, and then all divided by radical x plus 1 squared. I don't know what that is, but let's add another page. Okay, so now, interestingly enough, let's see, the rad x goes away, and the negative rad x goes away, and the 1 and the -1 go away to make 0. To make 0 is the answer? Oh, that can't be right. Something went wrong. Let's look at that book. What does the book say? Probably not that the answer is 0, right? 31, the answer is 1 over rad x times rad x plus 1 squared. So I definitely made some kind of illegal math move. Let's go find it. Let's put this back to full screen. Thank you. Okay, let's look. You lost a negative in that step. Let's see. Thank you, Amanda. Let's see if we can find that negative that I lost. Oh, is this the negative I lost right here? So it's rad x plus 1, and then it's, oh, I did lose a negative. Thank you, Amanda. You are a lifesaver. It's this negative right here that I lost, gang. This negative should have been distributed to the radical x minus 1, making this not a negative 1 here, making this a positive 1. And that, therefore, would not cancel with that positive 1. That would just simply make 2. That would just simply make 2. So this is now 1 over 2 radical x times 2, all divided by radical x plus 1 squared. Ooh, and that's actually quite convenient. Check this out. 2 and the 2 cancel each other out. And I'm just going to take this radical x, and I'm just going to move it right to the bottom, because that's just 1 over radical x, which is the same thing as radical x in the divisor. So this is just radical x times radical x plus 1 squared, which I think is the textbook's answer. Let's just check. Cool. So that was a good one. All right. I hope that helps. You forgot to show me the other one. Yes. Thank you so much, Trevor. I appreciate that. It's definitely easy to lose a negative somewhere in a long algebra problem like that. But I think we got it. Okay, ladies and gentlemen, I hope what is this, our fourth review together was helpful. We'll certainly be working on the review packet. Just so you know, I have posted the answers to it online already. Please take a look as you start to solve the problems, and let me know if you have any questions or concerns in class. We'll start to take a look at it together, making sure everything is all set. All right? Great. Well, I hope everyone enjoys their night. Thanks so much for hanging out with me. And if you're tuning in later, I hope this was helpful, and have a good night. Oh, no, can't stop that. Got to stop YouTube. Just turn off my camera. There we go.